So although I said this topic's mainly, again, concerned with proofs, there is sort of like the other side of things where we're just looking at the graph itself and learning how to do maths and interpret these graphs. Okay, now let's have a look at the different types of graphs that you will come across in this topic. So first we have simple graphs. So simple graphs are graphs that have no loops or multiple edges between the same set of vertices. So for example, for A and D, there's only one line that connects them. So there's no multiple edges, so no more than one edge connecting a particular set of vertex. That's basically the only rule for a simple graph. So the second one you can see here, over here, is not a simple graph because it has multiple edges, also has loops. So these are all features that are not common to simple graphs. Then we have isomorphic graphs. So if you do chemistry, you might have heard of isomers or just the prefix iso. So iso just means equivalence or different forms. Different forms of the same thing. So an isomorphic graph has the same connectivity between nodes, although it might be arranged differently. So basically, it's just another way of representing this graph that looks a bit different. And the way that it might be useful is for something called planar graphs. Or for example, maps, a really good application of this. So we might just have a common map, and then we might draw an isomorphic graph just to make the map a little bit more useful. So really, really important sort of stuff. And just a sort of disclaimer for this topic, the length of the lines does not matter most of the time. The length does not matter. So for example, for E and B, this one's short, this one's long, does not matter. It's the same graph. It's an isomorphic graph. It's the connections that we're looking at. Is B connected to E once, twice, or connected or not connected at all? That is what we are checking to see if we have an isomorphic graph, not the actual length of the lines or the edges. Just something a lot of students get confused with. Then we have subgraphs. So subgraphs are smaller graphs that are part of larger graphs. Now, obviously, I can imagine a lot of applications of a subgraph in real life. So for example, if we have, an Australian map, so a map of the entire continent of Australia, and let's just say we only need a map of, the city, Melbourne City, CBD. So that would be a subgraph of the main graph, for example. A very sort of practical example. So subgraphs look the exact same. So we're not drawing isomorphic graphs in this case. We're going to draw the exact same thing, just removing stuff from the original graph. So for example, all of these are subgraphs of this parent graph. Next, we have connected graphs. So connected graphs are basically graphs where we have no isolated vertices. And an isolated vertex is basically a vertex that has no edges connecting it to other vertices. So a connected graph will have no isolated vertices. We will have connections to every single vertex on the graph. And there is a rule for a connected graph. So the number of edges in a connected graph is always equal to the number of vertices minus 1. Sorry, not always. This is the minimum number of edges that we need. The number of vertices minus 1. Any more doesn't matter. Any less, it's not a connected graph. Next, we have complete graphs. So complete graphs is basically a type of connected graph in which every vertex is connected to every other vertex by an edge. So A, for example, would be connected to B, C, D, E. B would be connected to A, C, D, E. So that's why it's called a complete graph. Everything is connected to everything else. It's complete. There can be no further edges added unless we're creating, something that's not a simple graph. Yeah, so essentially that is what a complete graph is. It's a simple graph where every vertex is connected to every other vertex by an edge. There is a rule to work out the number of vertices in a complete graph. And remember, this is a simple graph as well. So no multiple edges, no loops. So basically, the rule is n minus 1 over 2. So n represents the number of vertices. So to work out the number of edges in a complete graph, all you need to do is take the number of vertices multiplied by the number of vertices minus 1 divided by 2. For example, in this one, instead of counting every single edge, which can get really painful, just count the number of vertices, 1, 2, 3, 4, 5, and apply to this formula. So it will be 5 times 4 over 2, which is 10. So therefore, there will be 10 edges in this graph without counting.